Hey kids, today we're going to talk about section 5, which deals with linearization. The other one in there is Newton's method. We'll look at that in just a minute. Both of these, though, require kind of a repetition of a pattern. So they're really not super difficult to work through. However, if you make a small mistake somewhere, man, you'll pay for it later because your mistake will grow as you work through the process. And with both of these processes, I come back to long division. So if you've got like 65 and you do some long division into 3,286, you've got to figure out how this works. So you're going to start with like maybe 4 or 3 or I don't know, and you multiply, and then you carry 2, and that's totally not going to work because that's too big. But you get the point here. So then you subtract and get a thing, and 720 or whatever, and then bring down an 8. So it just goes on and on and on. Well, when you do linearization, you're taking a pattern and repeating it, and so we just need to figure out what that pattern is to go with it. All right, and what the pattern does is it tells us if we've got a differentiable equation at a specific point, we can take a derivative at this specific point, then we can find the tangent line by looking at the function at that point times the derivative at that point times x minus whatever that point is. And that will give us the equation of the tangent line. It's actually really kind of a cool little thing. All right, so this is called linearization of f at a, and the approximation, little f of x is equal to capital L of x, is the standard linear approximation of f at a. So the point x equals a is the center of the approximation. And basically what we're saying is if you zoom in really close at this point where we're looking at a tangent line, really close on that point, when you look at a graph of that, it looks like a straight line. So even if we had the graph of a parabola here, if you zoom in on just this point and you zoom in far enough and you zoom in far enough, this part right here where we're interested is going to look like a straight line. So that's what we're wanting to do. All right. So find the linearization of f of x equals 1 plus the square root of 1 plus x, where x equals 0. Use it to approximate 1.02 without a calculator. So this is actually kind of a cool trick. What we need, though, if you'll notice that we're talking about x is equal to 0. All right. So that's a piece that we're going to need. And we can plug that in right now if we want. So f of 0 is equal to square root of 1 plus 0, which is 1. So we know then that the center of all of this is going to be the point 0, 1. This is our center spot, okay? And that's going to be the center of the approximation is that guy right there. And then what we're going to do is we're just going to find the derivative real quick. So I'm going to rewrite f of x so that it looks a little bit more derivative friendly, which is 1 plus x to the 1/2 power. So the derivative of this is 1/2 times 1 plus x to the negative 1/2 power, and then times the derivative inside for chain rule purposes, but that's just a 1. So what I end up with is 1 over 2 times the square root of 1 plus x. That's my derivative. That's this part right here. We just found this part right here. So now I need the derivative at 0. And that's going to be this whole part right here, the derivative at 0. That's that guy. Okay, and so that's going to be 1 over 2 times the square root of 1 plus 0, which is going to be 1 over 2 times the square root of 1, which is 1 over 2. So there's that guy, all right? So the linearization then, the linearization, L of x, is going to be equal to 1 plus f prime of that times x minus 0, which in this case is just going to be equal to 1 plus 1/2 x. So that's the linearization at the center of all of this, of what's going on. So what are we doing? We're taking the square root of 1 plus x and graphing it. We're looking at 0, and we're finding a tangent line at that point. When we get to that tangent line, it would be represented by this guy right here. So if we zoom in close enough to our graph, that's what it's going to look like. Now, we want to approximate the square root of 1.02. So what we're going to do then is we're going to look at all this information again, but now instead of f being 0, we're going to look at f of not 0 anymore, but what? F of well, let's look at it this way. Let's just back up for 1 second. If I have 1 plus x, and I want this guy to equal 1.02, guess what x is on this particular guy? And we're going to see that x is 0.02. So what does that mean? That means now everywhere we had a 0 just a second ago, we're going to put a 0.02 in for x. And it's going to change things around a little bit. So we're going to borrow from this guy right here. All right, we're going to borrow from this guy. And so what I'm going to get when I do this is f of, I need f of 0.02. And it's going to be equal to, let me think how I want to say this. This is going to be equal to the linearization of 0.02, which is going to be equal to this guy right up here. And so what's going to happen is you're going to have 1 plus 0.02, the x, divided by 2. And when you look at this guy right here, that's going to be 1 plus 0.01. So your linearization is that guy. Notice the only thing that changed was right here, my x value. My x value becomes 0.02. So I follow that same process. I just don't need to do all that work again. There's no point. I've done the work, and then I get over here, and when they say, hey, check out, you know, how close are we to this guy? Well, we're off by 0.02. That's my new x, and I substitute it in for x, and now I'm off and running. So you can calculate 1.02 with a calculator, square root of 1.02, and it's going to be close to 1.01, believe it or not. So this is kind of a handy way to kind of do some fun stuff. And again, this is a process. It's going to be this step, then this step, then this step. So when you're working a problem like this, do it that way. Take this step, then the next, and then the next. And this can be a difficult concept to kind of grasp, but if you practice it, eventually you'll understand exactly what you're doing. But until you kind of get to that understanding point, I would work the same problem out a couple times. See if you can get the exact same answer I got on your own, and then come back and double check it. Okay, so now we want to find the linearization of f of x equals cosine x, where x equals pi over 2. Use it to determine the cosine of 1.75. And again, let's just remind ourselves of that linearization, what it looks like. And so I'm just going to borrow from the old buckaroo here. L of x is equal to f of a minus f prime of a times x minus a. So there you go. In this case, a is going to be pi over 2. All right. So we know that that's where we are headed, and we just need to know a couple things. We need to know the function at pi over 2. So f of pi over 2, that's going to be the same thing as the cosine of pi over 2, which is 0. Hey. And then what else do I need on here? I've got f of a. I need f prime of a. So I need the derivative of x, which the derivative of the cosine is negative sine x. And then I need the derivative at pi over 2, And at pi over 2, that's going to end up being, should be negative 1. So what's the linearization looks like? Well, L of x is equal to f of a, 0, plus f prime of a, negative 1, times x minus a, x minus pi over 2. There you go. That's all there is to it. How hard is that? Not hard. So we would simplify this just by saying negative x plus pi over 2. That's my linearization, right? Is that what they get in the book? Yes. Okay. So now what? Now they want us to find this linearization and use it to determine the cosine of 1.75. The cosine of 1.75, how do you do that without a calculator? Man, I don't know. But I do know this. They're telling me that my new x, what took the place of the x here? What took place of the x? X is now going to equal 1.75. So after we've established our linearization, which in this case is negative x plus pi over 2, all we have to do is put negative 1.75 in for x. I'm sorry, the positive 1.75 in for x. So we could write it this way. The cosine of 1.75 is equal to the function of 1.75, which is equal to the linearization of 1.75. And when I say equal to, these are approximations, because that's what we're doing. We're approximating. Well, if I already have a linearization of x, that's this guy. The only thing that now changes is the x. The x becomes 1.75. So now what I'm going to end up with is negative 1.75 plus pi over 2. So there you go. That's a good answer for me. I'm okay with this. If you wanted to clean it up and say negative 1.75 plus pi over 2, you could do that, because the whole goal here was to kind of do this without a calculator. If you wanted to be like one of those uber cool kiddos, you could punch this into your calculator and give me another approximation, but this is an approximation with an exact part to it. So this is like a good answer if you were doing it in my class. And again, check with your teacher, but also this is a process. Like, what process did I take? And if you don't understand it right off the bat, that's okay. Just practice this. See if you can get the same answers that I got by doing this problem again. All right, what we're going to look at this little section of stuff is how we can, let me give you the definition your book gives it. This is approximating binomial powers, okay? So that's what we're going to do here. We're going to approximate a binomial power. This is actually pretty cool. So if we've got this form of a shape, we're going to have this linear approximation, okay? And that's how it's going to work. So if we're looking for a linear approximation of some sort of binomial power, doesn't matter what the power is, then we're just going to follow this pattern. So we've got some problems here. We've got 1 minus the cube root of 1 minus x. So let's just rewrite all these so that they match our generic example. So this guy would look like that. This guy right here is going to look like this. This guy right here. Now notice it's x to some power, so this is going to be a two-stepper probably. But look at this. We've got 1 plus 5x to the 4th to the 1/2. But I need just an x there, so what do you think on that? I don't know. I feel like something maybe interesting happening here. We'll check this one. And then this guy is going to be 1 minus x squared to the negative 1/2. So that's what you got. 1 plus kx. So in this case, k is 3. So 1 plus kx is just going to be 1 plus, this actually should be 1/3 here. 1 plus 1/3 times negative x. So you're going to end up with 1 minus x over 3. That's your approximation. That's all there is to it. Okay? Easy peasy lemon squeezy. What about this guy right here? So this guy, k is equal to -1. Let me just, this is bothering me. This should be a 1/3. So k is -1 here. So what are we going to have? We're going to have 1 plus k times x. So 1 plus x is how this one should turn out. All right, what about this guy down here? So this is going to be 1 plus, and then on this guy, if you'll notice, it's going to be the 1/2, and then times to whatever's in the x spot. So that this whole 5x to the 4th, that whole thing is in the x spot, and so when we do him, oh, I messed up my color here. When we do him, we're going to end up with 1/2 times 5x to the 4th. So that's going to give me then 1 plus 5/2 x to the 4th, or 1 plus 5x to the 4th over 2. All of those will work. All those work. The last one then, we've got that -1/2 up there, so 1 plus k times x. And so this guy's going to end up being 1 plus 1/2 x squared. And the same thing on this one, you could also say 1 plus x squared over 2. But that's how you approximate make an approximation of a linear approximation with this special binomial situation only. It's really kind of a cool deal. All right, now this example is not in your notes. I forgot to add it in there, but it's one that's very similar to the first example that we did. So I thought this would be a good kind of review of linearization, just more practice so that you can see some different problems. But we want to use linearization to find the square root of 123. Now remember, linearization, if you go back to that first slide, linearization of x is going to be the function of a minus f prime of a times x minus a. So basically what we're going to have to do is figure out the derivative. So of what? Well, the derivative of, let's treat this guy as a function of x. So f of x is equal to x to the 1/2, and we'll come down here and we'll say f prime of x is equal to 1/2 x to the -1/2, or 1 over 2 square roots of x. Okay, so this is our initial setup. The rest of what are we going to do and how are we going to do it becomes a little bit tricky. So what we've got is a situation where we've got x equal to 123. Well, I know, I don't know the square root of 123. I don't know. Okay, this is what we're trying to find out. But a square root that's really close to that is 121. So what if I let x equal 121? That's pretty close to 123, you know, in the grand scheme of things. And so the square root of that is 11. And if I do that again, I could have the, let's see. That's going to be 1 over 2 times 11. So I've got kind of these two parts, but how far then do I have to go to get to 123? And that would be, I'm going 2 spots. So if my A is 121, holy smokes, where'd my stuff go? There we go. So what I'm going to do is I'm just going to follow this right here, and I'm going to have 11 minus f prime of a, which is 1 over 22, times x minus a. What is x? X is 123, minus a, which is 121. So there's your setup for that guy. Pretty painless, actually. We're just going to follow that pattern that we've been given. So 123 minus 121 is 2, so 11 minus 122 times 2 is going to be 11 minus 1 over 11, which is, I don't know what that is as a fraction, would be 120 over 11. Is that right? And then 120 over 11, since we're trying to determine the square root of 123, we'd do 120 divided by 11, and I get 10.909. Okay, it would sure help if I could punch my stuff in correctly, because this should be pluses all the way around. Yikes. So when you add all this up, it's going to work out perfect. So 121 plus 1 is 122. 122 divided by 11 is, and I quote, 11.09. So there's using your linearization. It's really kind of a fun thing to do. You could use cube roots or fourth roots or fifth roots or whatever root you wanted to find. You could use something you know to find something you don't. It's kind of exciting. All right, Newton's method. This is really a cool thing, a cool way to approximate zeros. It's really kind of fun. And again, it's a pattern. So if you kind of mess up somewhere at the beginning, this could throw you off at the end. You'll need one of these bad boys to work out a Newton's method, because you're going to have to do some really heavy calculating on your calculator. But it really isn't too bad. It's I think, fascinating how quickly we can approximate a zero using Newton's method. Let's just take, for example, x cubed plus 3x plus 1 equals 0. That needs to be plus 1 equals 0. Now, if we want to approximate zeros on this, we need to kind of get ballpark-ish of the zero, all right? And to do that, you may need to look at a graph, and if you can just get ballpark-ish, we don't have to be identically right up on the thing. We don't need that either. We just need to be in the ballpark. Your Newton's method will trend itself towards the closest zero. So depending on how close you are, just depends on how many times you'll have to cycle through Newton's method. It's a repeating cycle. You're going to guess an approximation for f of x equal to 0. Then you're going to use the first approximation to find the second. Then you're going to take that second approximation and find the third. Then you're going to take the third approximation to find the fourth, and then the fourth to find the fifth, and so on. And you can do this, and fairly quickly you wind up with a very close approximation. Sometimes you might have to go 3 times. Sometimes you might have to go 5. To get an approximation within several decimal places, but it's really a pretty doable thing. So here we go. We're going to need a derivative, because that's our formula is going to be our first guess minus the function at that guess divided by the derivative at that guess. So we're going to need a lot of zeros here. So if you want to look at the graph of this, fine. If not, fine. I'm going to start off, and I'm going to let x, my first x1, be equal to 0.3, negative 0.3. All right, this is a good safe number. And so what I'm going to do is I'm going to do the function at negative 0.3, and I'm going to do the derivative at negative 0.3. Now, one thing that you may want to use on your calculator that can help with this, there's a couple tricks that you can use. And one of the tricks that's easier right off the bat is to store negative 0.3 as an x value, and then you can just type in x cubed plus 3x plus 1, and you can type in 3x squared plus 3. So that's just one way to do it. When I punch this into my calculator, I do all this math, I punch it all in, and I get at the end when I do x, let's see here. Let's see, store negative 0.3. We'll just store that bad boy as x. And then x cubed plus 3x plus 1 is 0.073. And 3x squared plus 3 is 3.27. So to get my first approximation, I'm going to do negative 3, and then that's my first guy. So minus the function divided by the derivative. And on some of this, you may want to carry through a few decimal places just to be as accurate as possible. Let your calculator find as many decimal places as possible. So when I do that, I get my next approximation, x2, which is going to be negative 0.322 Now I'm carrying several decimal places here because we want to determine this as close as possible. And I think, like in your book, you're going to actually carry it through to 8 decimal places. So this is a really close approximation. Then we're going to do the same thing again. So just store that number as x, and then take the same process that we just took. And once you do that, you'll get your next guy. So and I just went ahead and punched this part in right here. This part became negative oh shucks, that can't be quite right. Oh darn it. I got it this time. Becomes negative 0.123138798, and a whole bunch more. So what we're going to do is we'll take our second 0 minus that guy, and we'll get our third one, and it's going to be even closer. So what I'm going to get is that guy minus that guy. And so my third 0 is x3. And again, you can punch all this in and store it in your calculator. It makes it easier. And then we'll do it again, and I'll just tell you on that one, when you punch it in, let's move these guys up a little bit here. So when I do the fourth guy, then I'm going to end up with negative 0.322185 3 5 4 6. Look how close that we lined up here, all the way to that point right there. So this is called Newton's method, and again, it's just a pattern. Just repeat, 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 and you'll get closer and closer and closer, and you'll eventually get to that 0. All right, this also is out of your note packet. I'm sorry about that. The mad scramble to get things done. I omitted a couple of things, but Don't worry, I've got you covered. So differentials, what is that? That's the dy dx part of the derivative. So let y equal f of x, and it's going to be a differentiable function. The differential dx is an independent variable. We treat it like its own little thing. It goes together. And the differential dy is equal to dy equals f prime of x dx. Think about this. If I have y equals f of x, then dy dx is equal to f prime of x. The cool thing about this is I can treat all three of these pieces uniquely. I can treat dy as a unique piece, dx as a unique piece, and f prime of x as a unique piece. So all I'm going to do to get dy all by itself is multiply both sides by dx. And that's how we get this formula right here. It's actually kind of cool. And it's important because we use this a lot when we are using integrals. So let's just look at a couple things real quick. What if I said to you, hey, I've got y equals x to the fifth plus 37x, x to the fifth plus 37x. Find dy if x equals 1 and dx equals 0.01. Well, hey, guess what? Remember just a second ago I said we've got three pieces. We've got 1, 2, 3 pieces. I need 2 of those pieces to find the third. So all I'm going to do is take the derivative here, so y prime. Let's actually do it this way. Let's say dy dx. And what does that equal? That equals 5x to the fourth plus 37. Okay, there's that guy. But I need dy, so I'm going to multiply both sides by dx times dx times dx. And it's not just 37 times dx, it's the whole thing times dx. So dy is equal to 5x to the fourth plus 37 times dx. Now, all I need to know is what my x value is and what my dx value is, and I'm off and running. That's all there is to it. So dy is going to be equal to 5 times 1 to the fourth plus 37 times 0.01. That's it. So 5 plus 37 times 0.01. 5 plus 37 is 42 times, actually, since we got that decimal, 0.01. And what is that going to be? 0.42, I think, is what that one's going to end up being. 0.42. Yep. So that's how you do that. So if you're given a question like that, it's not a problem. You can find different things about area. You can find different things about relative percent when you look at all this. So this is really a cool tool to have because it allows us to isolate one of those variables, the dy or the dx variable, to solve for all the other parts. And remember, the dy and the dx, that's just the change in y and the change in x. So if x changes by 0.01, how much does y change at the same spot? And that's all there is to this part. So on this time, what we're going to do is we're going to work with the notation that f prime is going to be equal to dy dx. That's going to help us the most with this particular set of problems because then that gives us those two separate pieces. Okay? Good luck.